The last topic that we'll cover for Chapter 1 is the ever so simple yet ever so useful concept of reference angles. Here's the definition of a reference angle. If theta is a non-quadrantal angle, that means theta is not going to land on an axis. It's not going to be a multiple of 90 degrees or a multiple of pi over 2 radians. So if theta is a non-quadrantal angle in standard position, then the reference angle for theta is the positive acute angle theta prime, the apostrophe there we read as a prime, formed by the terminal side of theta and the positive or negative x-axis. So first thing to note is that reference angles are always positive and acute. So reference angles will be some sort of quadrant 1 angle. The reference angle is made from the terminal side of the angle and the nearest x-axis. So we have several diagrams here to illustrate this concept. In the first diagram, we have an angle theta, which is an acute angle landing in quadrant 1. So it is its own reference angle. Or you could say theta doesn't necessarily need a reference angle. In the second example, we have an angle theta that is between 90 degrees and 180 degrees. So we have an example of an obtuse angle here. So the reference angle is going to be made as the acute angle composed of the terminal side of theta and the nearest x-axis. So if we wanted to find the measure of this reference angle theta prime, notice we could start here at pi radians and subtract theta. So that's what we have right here. If we want to think about that in degrees, we could say theta prime is 180 degrees minus theta. On the next example, we have an angle in quadrant 3. So theta has its terminal side here in quadrant 3. So the reference angle for theta is going to be the acute angle made from the nearest x-axis and the terminal side of theta. If we wanted to calculate the value or the size of theta prime, notice we could start from pi, or start from theta and subtract pi, and that's going to give us the measure of our reference angle. So theta prime is equal to theta minus pi, or in degrees, we could say theta prime is equal to theta minus 180 degrees. The leftovers right here defines our reference angle. Finally, if we have a quadrant 4 angle, then the reference angle will be made with the positive x-axis. Looking at the angle 2 pi and subtracting our angle theta, that's going to give us the size of our reference angle. Or we could say theta prime equals 360 degrees minus theta. Now you're going to find out this is a little easier with specific examples maybe than looking at it in general. So let's work example 3. For each given angle theta, sketch the reference angle theta prime and give the measure of theta prime in both radians and degrees. So we'll begin with the angle 135 degrees. I'm going to start by constructing that angle in standard position. So we're going to draw our XY rectangular coordinate system. 135 degrees lands in quadrant 2. So in standard position, we have 135 degrees over here. So this angle is theta equals 135 degrees. So we can see that theta prime would be this angle right here. So to calculate the value of theta prime, we're going to start with 180 degrees and we're going to subtract 135 degrees. That difference there is 45 degrees. So our reference angle theta prime in degrees is 45 degrees. We could also recognize that in radians, theta prime then is pi over 4. Either you have that memorized or you remember that you can multiply 45 degrees by pi over 180 degrees and reduce, and you'd end up with pi over 4. Let's try the next example. On example B, we have the angle 4 pi over 3. So we begin by sketching this angle in standard position in our rectangular coordinate system. Hopefully you're becoming very familiar with all the common angles, but in case you haven't yet, let me remind you of how to count your way around the unit circle to get to 4 pi over 3. Remember that pi over 3 is a 60-degree angle, so I'm going to count in multiples of 60 degrees. So that would be 1 pi over 3, 2 pi over 3, 3 pi over 3, and we would land here at 4 pi over 3. So our angle theta in standard position, 4 pi over 3, lands in quadrant 3. So our reference angle will be made with the nearest x-axis. So this right here is going to be our reference angle theta prime. To figure out the value of theta prime, we're going to take our angle theta and we're going to subtract pi. We're going to subtract this amount from our entire rotation theta, and that's going to leave behind the value of theta prime. So let's evaluate 4 pi over 3 minus pi. We're going to need a common denominator, so we'll take 4 pi over 3 minus 3 pi over 3, and we can see that's going to give us the reference angle of pi over 3. Now, notice how compatible pi over 3 is with 4 pi over 3. You're going to see lots of similarities in the denominators when you're dealing with radian measure. If we wanted to express that in degrees, pi over 3 in degrees is equivalent to 60 degrees. Either you have that memorized or you remember you can multiply by 180 degrees over pi to convert that radian measure back to degrees. Let's try a reference angle for something that's greater than 1 rotation. So we have 780 degrees for angle theta, and we want to find the reference angle theta prime. So first of all, quickly notice that if we take 780 degrees and we subtract 2 rotations, that is 720 degrees, 2 rotations of 360 degrees each, this angle is coterminal with 60 degrees. So 780 degrees in standard position begins at the positive x-axis and it rotates once, that's 360, twice, that's 720, plus another 60 degrees, landing here in quadrant 1. So this is our angle theta equal to 780 degrees, coterminal with 60 degrees. Because the reference angle is made here with the positive x-axis, and we have already determined that it's coterminal with 60 degrees, we can see that theta prime then is equal to 60 degrees. Converting that to radians, we could also express that as pi over 3. So we're kind of picking on 60 degrees and pi over 3 in these last two examples. Let's determine a reference angle for a negative angle. Remember, a negative angle rotates in the clockwise direction. So we need to locate the terminal side of negative 5 pi over 4. Remembering that pi over 4 is a multiple of 45 degrees, or equivalent to a multiple of 45 degrees, I'm going to count my way around the unit circle in multiples of pi over 4, or thinking 45 degrees, to find negative pi over 4. So this would be negative 1 pi over 4, negative 2 pi over 4, negative 3 pi over 4, negative 4 pi over 4, negative 5 pi over 4. So I show you that just to enhance or give you a way to verify your memory. Hopefully you've memorized the location of positive 5 pi over 4, so you can reverse that and find the angle negative 5 pi over 4. We see that it is a quadrant 2 angle. Our goal here is to find its reference angle. From the diagram, we can see that the reference angle will be made with the negative x-axis, so we need to calculate theta prime. To calculate our reference angle theta prime, this time, because we're dealing with a negative angle, we're going to add pi. So if we've rotated through a negative angle and then we add pi, the difference here is going to be our reference angle. So we're going to take theta negative 5 pi over 4 plus pi When we get a common denominator here, we have negative pi over 4 plus 4 pi over 4, and that's going to give us a reference angle in radians of pi over 4. And in degrees, that's equivalent to 45 degrees. Now, the diagrams are certainly helpful, but look at the big picture. Whenever we wanted to find a reference angle for something that had a 3 in the denominator, the reference angle was pi over 3. In this case, we were finding the reference angle for something with a 4 in the denominator. In this case, the reference angle was pi over 4. If we had an example here of a radian measure with a 6 in the denominator, the reference angle would be pi over 6. So watch for those patterns. That will help you to get to know your reference angle. Now, reference angles are going to be very useful as we learn how to calculate sine, cosine, and tangent for every single angle, common angle on our unit circle. So let's make an observation about the relationship between the trig function evaluated at an angle theta and that same trig function evaluated at the reference angle theta prime. So this theorem states that for an angle theta in standard position that is not a quadrantal angle, sine of the original angle theta is equal to sine of theta prime, either the positive or the negative. Okay, it's not equal to both. It's saying that sine of the angle theta is either positive sine of theta prime or negative sine of theta prime. And you're going to see this is true for all 6 of our trigonometric functions. So the idea is that the trig function evaluated at the original angle theta is going to have the same absolute value of the trig function evaluated at the angle theta prime. We will choose the correct sign based on the location of the angle, in which quadrant it lands. So theta prime is the reference angle for theta. The sign is determined by the quadrant in which theta lies. So let me explain this a little more clearly in the form of an example. 1. Example 4. Find the sine and cosine for each angle using reference angles. First, notice that all of the angles that we're looking at in example 4 are the same as the angles that we considered in example 3. So we've already found their appropriate reference angles. So let's go ahead and list those. For 135 degrees, the reference angle is 45 degrees. For 4 pi over 3, the reference angle is pi over 3. For 780 degrees, we found the reference angle theta prime to be 60 degrees. And for theta equals negative 5 pi over 4, we found the reference angle theta prime to be pi over 4. So in order to evaluate sine and cosine for the given angle theta, we need to be able to evaluate sine and cosine for the given angle theta prime. We can either do that using special triangles or a table of values. For convenience sake for this problem, I'm just going to make a table of values down here at the bottom of the page. So let's consider all of our common angles: 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Reference angles for common angles will be those quadrant 1 angles. 0 and 90 are not included, but we might as well practice them here. So let's find sine of each angle and cosine of each angle. Sine of 0 degrees is 0. Sine of 30 is 1/2. Sine of 45 is square root of 2 over 2. Sine of 60 is square root of 3 over 2. And sine of 90 is 1. Cosine of 0 is 1. Cosine of 30 is square root of 3 over 2. Cosine of 45 is square root of 2 over 2. Cosine of 60 is 1/2, and cosine of 90 is 0. Once again, you can obtain those values either using special triangles or using the hand trick that we've talked about. Now that we have that table for reference, let's go back and find the sine and cosine for each given angle. So in example A, we need to find sine of 135 degrees. Now notice that 135 degrees is in quadrant 2. In quadrant 2, sine is positive. So sine of 135 degrees is going to be equivalent to sine of 45 degrees. Sine of 45 degrees is the square root of 2 over 2. So sine of 135 degrees and sine of 45 degrees have the same sine value. Let's think about cosine of 135 degrees. Now, cosine of 135 degrees is either going to have the same value as cosine of 45 degrees or the negative value. So in quadrant 2, the value of cosine is negative. Okay, so cosine of 135 is going to be negative. For our quadrant 1 angle, cosine is positive. So we're going to recognize that cosine of 135 degrees has the same value as cosine of 45, but the opposite sign. Cosine of 45 is the square root of 2 over 2, so we end up with negative square root of 2 over 2. Let's practice that again with theta equals 4 pi over 3. Recall that 4 pi over 3 is a quadrant 3 angle. In quadrant 3, both cosine and sine are negative. So if we want to find sine of 4 pi over 3, then we're going to have to find the negative sine of pi over 3. Sine of pi over 3, remember pi over 3 is 60 degrees. Sine of 60 is square root of 3 over 2. So we're going to end up with negative square root of 3 over 2 for a quadrant 3 angle. Cosine of our given angle 4 pi over 3 will be in terms of cosine of the reference angle pi over 3. However, in quadrant 3, cosine is negative, so we're going to find the opposite of cosine of pi over 3. Cosine of pi over 3 is a half, so cosine of 4 pi over 3 then will be negative 1/2. Moving on to 780 degrees. 780 degrees we discovered is a quadrant 1 angle. So its sine and cosine will both be positive. So 780 degrees is going to be identical to sine of its reference angle 60 degrees. Sine of 60 degrees is square root of 3 over 2. Cosine of 780 degrees is going to be identical to cosine of 60 degrees. They're both quadrant 1 angles. Cosine of 60 degrees from our table is 1/2. Finally, pi or theta equal to negative 5 pi over 4 we discovered was a quadrant 2 angle. In quadrant 2, sine is positive. So sine of negative 5 pi over 4 is going to be the same as sine of its reference angle pi over 4. Sine of pi over 4 is square root of 2 over 2. And for our last problem for chapter 1, let's evaluate cosine of negative 5 pi over 4. Now in quadrant 2, where negative 5 pi over 4 lands, cosine is negative. So this is going to be negative cosine of its reference angle pi over 4. So that's going to give us negative square root of 2 over 2. The idea of reference angles is that every single angle, every common angle on the unit circle can have its trig functions evaluated in terms of those quadrant 1 angles. So when you know this information, sine, cosine, and even tangent of the quadrant 1 angles, then all you have to do is adjust the SIGN for angles in other quadrants using reference angles. It takes some practice, but it's a very efficient way to evaluate your trig functions.